James. I'm at Aarhus University, and this is joint work with Bernardo, our former the presenter from before, who was also my PhD advisor, and Mariana Gama from Leuven, and Christian Janos Lebeda from the BARC algorithms group in Copenhagen. So the title of the talk, as Valeria said, is on correlated output differential privacy and applications to dark pools. So the first slide is kind of to set the motivation for this paper. So here we have a setting which we call the trusted curator setting. We have three parties who provide inputs to a trusted curator. They have secure channels to this curator, so these are private inputs. And the curator then computes something, some function on these inputs, and then provides private outputs individually to all three parties. And you can imagine a situation where we use this setting to implement a dark pool. So in this dark pool, we have parties who are submitting trades. Let's say we have the following trade format. If it's a 1-0, it's a buy. If it's 0-1, it's a sell. So we have party 1 that's submitting a buy, and parties 2 and 3 are submitting sells. And assuming you have some deterministic matching, a buy will always be matched with a sell. And in the classic application of MPC, we consider this private because the inputs are submitted privately. And the matching outcome is then submitted privately to the parties at the end of the round. In this work, we observe that there is leakage, though. So even though the input and outputs are private, one could observe the following. If the adversary corrupts a fraction of the parties, you can see that if the adversary observes a trade execution, there must exist some counterparty. That is, there must exist some counterparty for its first trade. So if I submit a buy and my buy gets executed, I must know that there must be some counterparty somewhere that submitted a sell. So this is what we coin output correlations. The outputs are correlated, even though they're private. For every buy, there must be some sell. And this is the leakage that we want to mitigate in this paper. So the question is, can we use some notion of differential privacy to protect the presence of the individual? And one of the aspects of this work is to observe that the standard notion of differential privacy is not sufficient for this notion. It's just a quick overview of our contributions here. So we observe that privacy leakage occurs in traditional dark pools. And this leakage comes from output correlation, a notion that's not captured by standard DP or standard differential privacy. In practice, why is this important? It's important because you want post-trade privacy. You want to execute a trade without the adversary learning that your trade actually got executed. For example, if you want to execute a trade strategy where you're taking a big order, breaking it down to small orders, which you then periodically submit, so some kind of time-weighted average price strategy, you don't want the adversary to anticipate that you're executing such a periodic buy or sell strategy. And with post-trade privacy, this is then guaranteed. There's some related work around differential privacy and AMMs in markets. So I cite two here. The first one is differential privacy in constant function market makers. There, the setting is a little different. So in this work, you have input privacy, but you don't have post-trade privacy. The same goes for the second work, kicking the bucket. This is an implementation of dark pools in MPC with quite impressive performance. But here too, there's no post-trade privacy. Every executed trade is output in the clear. So we contribute three things. We have a new definition for correlated output differential privacy, specifically for this setting. We contribute a protocol, a dark pool protocol, which is round differentially private, and round differential privacy we note as input and output differentially private. And we also private experiments. So we implement this protocol and we show that it approaches real performance, which is quite a nice result, I think. And I note that in this talk, we mostly talk about the setting with the trusted curator and MPC, but it's possible to cast our solution into the setting of private smart contracts with works like Eagle, Hawk, and so on and so forth. So the first slide, just to kind of recap the standard notion of differential privacy. So in standard differential privacy, you have a database including an entry from a single honest user. And this honest user can either include its entry or not include its entry. So it can kind of toggle its entry back and forth. And you have this analyst that's performed some query on the database, a deterministic query. Let's call this F. And the view of the analyst will be as follows. So if the user includes its input in the database, the observation will be this red one, and if not, it'll be this blue one. So there's some sensitivity in the analyst's output to the inclusion or non-inclusion of the honest user's input. So in traditional DP, if you have a differentially private query, you now have a randomized algorithm, and this randomized algorithm always outputs some output distribution, and this output distribution will still be sensitive to a change in the honest user's input, in our case, an inclusion or non-inclusion to the database, but the distribution, the probability mass for a given event will change by a bounded amount. That's the idea of differential privacy. So I'll have a different distribution depending on what the honest user inputs, but the change in the probability mass for a given event is bounded by epsilon. So in the first attempt, we're going to try to construct a dark pool that is differentially private, just with this traditional notion of input differential privacy. So again, we have the trustless curator. The trusted curator obtains these inputs. These could be trades, whatever the application. And we now have a differentially private mechanism that individually outputs distributions to all three parties, right? Because it's a randomized algorithm. So by definition of DP, outputs y1 to y3 are epsilon sensitive to the inputs. So the privacy of the inputs are guaranteed by differential privacy. But because if you have this scenario where the outputs are correlated, and in this case, I'm gonna show a arbitrary correlation. Here, the outputs sum to 0, so there's a zero-sum constraint on the outputs. Then if the adversary corrupts 2 and 3, given y2 and y3, the adversary learns y1, right? So because we have a zero-sum over the outputs, they're trivially correlated. And so the obvious solution here, and that's the main, if there's one takeaway from this paper, is the obvious solution is to bound the correlation between the outputs. So introduce some definition of differential privacy that bounds the correlation of the outputs in addition to the notion of epsilon sensitivity to the inputs. Okay, so the standard DP notion is kind of a cast in our setting of the trusted curator here. So in the standard DP notion, you have neighboring inputs, x and x prime. You have some adversarial output event SA, and you have output distributions induced by these neighboring inputs. And the difference in probability mass for a given event SA differs at most by the factor x epsilon. And this delta term here generally means that we relax the notion a little bit to obtain approximate DP, which means that with probability delta, the mechanism fails. But if delta is relatively small, that's something that we're willing to accept. In the same spirit, we introduce a definition called correlated output differential privacy, specifically for the setting of the trusted curator. And here we're isolating the influence of the honest user's output to the output distribution of the adversary. So we have fixed inputs given an output event SH, and the honest output distribution, which is the output from the mechanism for the honest user. For any, if the honest user gets an output event, and that output event is sampled in two different ways, the output distribution for the adversary should not change too much. It should be at most epsilon delta sensitive to a perturbation or change in the honest user's output. So it's the same spirit as the traditional notion of DP, but now applied to outputs. And so these two together, we say this is if a mechanism satisfies both definitions, it's round differentially in private. So input and output DP. So we design a mechanism to permit order matching, which satisfies these definitions. So for completeness, I have a sketch of the algorithm on the top, but I kindly ask you to just focus on the sketch at the bottom, the example at the bottom. So we have three parties here, P1 to P3, and they submit inputs. So buy, sell, buy, and consider a first step where we deterministically match these trades. So P1 gets matched with P2, a buy gets matched with a sell, and the third one is not matched with anybody, so it remains unmatched. So this is like the first deterministic step. And in our first attempt, we're going to do the following. We're going to say, this is the outcome of the deterministic matching stage. Subsequently, we're going to randomize the algorithm by sampling a true trade outcome. And if it was matched in the deterministic stage, it's going to be, the trade execution is going to be sampled with a higher probability. And so in this case, you might sample the following outcome. All trades get executed, even though in the deterministic case, only two were executed. So what does this mean? This basically means that P3 is executed, but it's not really matched with any counterparty, right? So we have a liquidity mismatch. There are more sells than buys, or vice versa. And so we have to patch this algorithm to kind of compensate for this liquidity mismatch. And we do it as follows. So I've pushed the randomized response to the left side. So if you look at the right side, you'll see the liquidity compensation mechanism that we introduced. So now we have a liquidity provider that at the beginning of the round submits R0, R1, a set of liquidity for both assets. And the liquidity mismatch is described here, is shown here. So 1 minus 1 for the two assets that are being traded or bought or sold. And what we do, though, is if the liquidity provider now compensates for this liquidity mismatch, the liquidity provider, in the naive case, will learn this liquidity mismatch, which is sensitive to the output of the individual user. So it's not output differentially private. To fix this, we introduce the following. We freeze an amount of funds from the liquidity provider in every round. So when the round is over, the liquidity provider will do the following. Thank you. It will have compensated for the liquidity mismatch, and it will also have some of its funds frozen, and the amount of funds that are frozen are sampled from a specific distribution. And so that way, the liquidity provider provides liquidity for the mismatch of buys and sells, but it also doesn't learn anything, or its view is only epsilon delta sensitive to the output sent to the honest user. So that's basically the main idea of the mechanism. We have parties that are matched in a deterministic fashion. The matching is then not output, but there's a randomized response run on top of it, giving us a randomized output. This induces a liquidity mismatch, which is caught by the liquidity provider. The liquidity provider then also has some of its fund frozen to ensure that its output view is differentially private, or correlated output differentially private. So I don't have too much time, so I'll skip the intuition for why the correlated output differential privacy aspect holds, but I refer to the full paper for that. And I note the following, that in our mechanism, there's a trade-off between privacy and the amount of funds that are frozen, amount of the liquidity provider funds that are frozen. So this distribution from which the freezing is sampled is parameterized by a parameter we call rho max. So at most, rho max assets will be frozen every given round. And as rho max increases, you obtain more privacy. And that seems intuitive, but so I have some, for example, we have some concrete parameters here. So if I say I'm willing to freeze up to 6 units, then I obtain the following parameters, epsilon 2.5, and delta being 5 times 10 to the power negative 4. So there, yeah, just to give you an example for how this trade-off occurs. This trade-off is independent of the amount of trades in a given round. So as the more trades I'm matching in a given round, the easier it is to kind of amortize this cost over multiple trades. Okay, I'm going to rush then. We have an implementation. This is, I think, a quite nice result as well. So we implemented this in a Scale Mamba MPC framework. And here we contributed oblivious matching protocols for MPC, so secret sharing MPC. And we used some tricks to be able to reduce the exponentiations required to compute part of the algorithm. I'll give you a quick data point. So if we're doing matching, if we're doing 1,000 trade matching 1,000 trades, we get 0.4 a runtime of 0.5 seconds. For like 7,000, it's at around 1.7 seconds. So we're really approaching, I think, practical throughput. So that concludes my talk. Just to recap, we look at dark pools. We observe that there is output leakage due to the correlation of outputs. And we fix this by introducing a definition of correlated output differential privacy. Output privacy matters for post-trade privacy and financial strategies like time-weighted average price, buying or selling. Yeah, that's my talk. Thank you very much.
Any questions for James?
Just there's
So from like the literature on privacy with mechanism design, there's like this notion of joint differential privacy. How does round differential privacy sort of correspond to joint differential privacy? And if you don't know it, we can talk offline.
Yeah, I don't know what joint differential privacy is. Does it have this notion of does it protect against outputs, or
it's basically like think of a mechanism. I get my portion of the output. Joint differentially privacy means that from my portion of the output, I can't learn more about the inputs of the other people.
Right.
So that sounds similar, if I understand.
Yes. Right. So in our mechanism, our mechanism is differentially private to inputs. What I think what we contributed is we relax the correlation between outputs. So if you have an output and I have an output, and they're always correlated, I may learn nothing about the inputs, but because I know that you will always, for example, obtain an output which is correlated in a specific way to mine.
I bought, you sold, so
exactly.
So even though I don't learn anything about what you wanted to do, from fact that I bought, I learned something.
And then you can infer in some cases, in this case, you actually infer the input as well.
Yes.
Right. So
you have. Okay, we can talk. Yeah.
Any more questions? Very quick question about your MPC. The results, the graphs you showed are for online phase. Do you have an estimate for the offline phase? Is it going to be much more expensive, or?
We just pre-process beaver triples, so whatever that overhead is, yeah. But you could parallelize that. So we say it's we just look at the online phase in our benchmarks. So.
Yeah, makes sense.
Yeah.
Great. More questions? If not, let's thank.